away we go. Well, assuming there's chalk here, kinda.
Blue
I
and
got
green.
some if you need some.
Well, trouble color chalk is it doesn't erase very well. Okay, so stiff differential equations. Okay, this is all right. Now, so we're very preoccupied with the order of accuracy of any time-stepping method, like how forward and backward Euler are both first order, trapezoidal method is second order, we have rugged cutter method that's fourth order, and etc. And similar discussion for multi-step methods. But what I want to make here is that order of accuracy is not the only thing to be concerned about. Because generally your error, if you have an error formula for any method, is basically approximated by some constant times h raised to some power. And we've been so focused on what is the power of p in your error, like we know what it is for Adams methods and so forth. And we have not discussed this constant c at all. And the thing is, what if that constant's really large? You could have a method that's, say, fourth order accurate, and your h is, say, 0.1. So your h to p is like 1 over 10,000. You think, oh, that's nice and small. But what if your c is like 100,000? Then your method is awful. So, and the thing is, this is not just for a particular method. It's really about the differential equation itself. That's why I'm not saying stiff methods. I'm saying stiff DEs. For certain DEs, your time-stepping method, say your Adams-Bashforth method, could be perfectly fine. And then you apply it to a certain stiff DE, and it fails. We want to try to have an understanding of this. So, do we know anything at all about C for any particular method? Yes, but not much. C generally has this form. Okay, now this is still for, it's some constant I'll call C0, which is usually of a reasonable size, times some derivative, higher order derivative of a solution at an unknown time. Actually, and then you have your, well, actually the h to the p I've already accounted for. So that's all. So really, that's what you're looking at. So C naught is fixed for each particular method. You can figure out what it is. I mean, you've seen examples from this from homework already. What that constant is. Okay, here's an example. Forward Euler. Your C naught is 1/2, and your K is 2. So it's the second derivative of your solution at an unknown time over 2 times H, because forward Euler is a first order method, and so on. So for given methods, these things are known. So the question we need to ask is, could this be large? Well, for a certain DE, absolutely they can be large. Okay. Now, here's where DE can get stiff And this will lead me to a definition of what it means for DE to be stiff and why it's such a problem. So problem 9 solution might be something like this. Maybe your exact solution has this form. There's a constant times e to the lambda 1t plus another constant e to the lambda 2t. Okay. And you've seen solutions like this from your DE class. For instance, solving a second order DE. I should mention, how do these kind of solutions come about? Not usually from a first order DE by itself, but from a system of DE. So when I say stiff differential equations, I'm generally talking about systems of DE, like that comes from a second order ODE, things like that. Okay, now let's make some assumptions. We'll assume that lambda 1 and lambda 2 are both negative. That way the solution is not growing over time. It's decaying to 0 at some rate. Then we'll also assume that lambda 1, this negative number, is okay. Just to make it easy, we'll assume it's much less than 1. So it's a nice small number. And that means slow decay to 0. So something like that. It's taking its time getting there. On the other hand, lambda 2, we'll assume it's much greater than 1. We'll have rapid decay. So, something like this. Dips to 0 very quickly. Okay. So, now let's focus on, I'm going to continue this example here, behavior of a solution. Because the second term with e to the lambda 2t, that becomes small very quickly. So your solution is dominated by just the first term. And because it's decaying to 0 so slowly, this is a smooth function. It's not changing very rapidly. So what does that mean? That means it's possible to represent this with a relatively large step size, h. Because you can evaluate it here, 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 connect the dots, and that captures your solution quite well. So you think, oh, everything's hunky-dory. I don't need to take a lot of time steps. I don't need to, this is faster. Because if you're using a tiny h, your time stepping method is crawling along, and you don't want that. We can compute the solution very quickly. Now, that's the behavior of the exact solution. But we're not computing the exact solution, we're doing time stepping. So now let's focus on the behavior of your error in whatever time stepping method you're using. Well, that involves some higher order derivative. So let's take a look at that. Kth derivative of the solution. Well, what's the derivative of that? These are exponentials, those are easy to differentiate.
So lambda 1, well, in terms of t, right? So lambda 1, c1.
Yes. Yeah, so what happens is you multiply by lambda 1 here. So for instance, okay, well, yeah, so y prime, yes. So if you just take this, the first derivative, and apply that k times, so you get c1 lambda 1 to the k e to the lambda 1t plus c2 lambda 2 to the k e to the lambda 2t. And this is evaluated at some unknown point. Now, how does the behavior of this derivative differ from the behavior of a solution? What is the dominant part now? Yeah, the second term, because even though both of these are going to 0,
Number 2 to the k is now bigger.
that's big. Now, eventually the whole derivative will still die out, but it takes a lot longer. Also, if we're at a certain time, we're out here, where the solution's supposed to be small, remember your error is controlled by a time that's less. So your derivative is being evaluated back here somewhere where things are still kind of large by comparison. So this is your dominant term. Now, so in other words, your C is now big. Here's your error. How do you offset a big C to keep your error under control?
Small steps back.
Yeah. To make this whole thing small, C is big, you gotta choose your H smaller. So this requires a small h. So that's going to slow down your whole time stepping method. Okay. All right. Now, all right, questions about any of this before I arrive at a definition of stiff?
What do you mean slower? Like slower decay to 0?
Well, in both cases, when I say faster here and slower here, computing time.
Oh,
The smaller your h, the slower your computation will be.
the more
Yeah.
number of steps.
And why did we say it was a small, it required a small h?
Because this is to offset the large constant, the large
Okay.
c in there.
Okay.
Yeah, because you want this bounded by some chosen accuracy threshold. Okay, so now we're in a quandary. You might think, okay, in order to represent the solution, I don't need a large h, but to compute it successfully, to compute it accurately, I'm forced to use it anyway. I'm forced to waste time. So it's a pretty awful situation. So when I put these two conditions together, the h we need to represent the solution, that's supposed to be h that I need to compute it accurately, that leads me to, close I get to a formal definition of what it means for an ODE to be stiff. It's not a precise definition, but it gets the idea across.
If you were computing that, would you compute them both for the same h or would you compute
What happens is, here's where it gets really pernicious, because especially if this is for a relatively simple DE, but for a more complicated DE, you may know you have these components, but you don't know the relation between them. You can't compute them separately because they're coupled together. Which actually is going to lead to my personal view on how you can get around that, which actually is what your research is all about.
that's fine.
Oh, okay. And yours
Yeah.
too. Okay. Yeah, this subject, it's a generic subject that all numerical analysis courses should cover, but it also leads to a rant about my research. Oh yeah, yours too. So it would also play into that.
Like how to get. Are you
No, I'm talking to the
talking?
campus.
Okay, yeah.
Okay.
He confused me with.
Oh, okay, yeah.
But then,
Yeah.
What's it? Okay, we'll talk.
Okay, yeah. Whatever I give you and you, the catch, will probably relate to that too. Oh, yeah, you also. So 1, 2, 3, 4, 5, 6 of the people in this room. Like I said, well,
The rest of y'all need to get with it.
I'm sorry.
anyhow, so a differential equation, or more properly, it really generally applies to a system of D. Because you don't really have this kind of phenomenon with a single first order ODE. They can't really have these kind of multiple components. It's stiff if a time-stepping method, whether it's implicit or explicit, whether it's one step or multi-step, doesn't matter. Requires a much smaller h to compute the solution accurately. Compared to the h as actually needed to represent the solution accurately. Okay, because if a solution changes rapidly, like it oscillates or decays to zero really fast, you need a small h to get an accurate representation. Because if you have something that behaves like this, as a sharp turn, and I use a large h to represent it, again playing connect the dots, I'm going to get this. That's not an accurate representation. I need a small h for that. Whereas if it didn't decay so fast, a large h should be fine. So, but the thing is, this kind of component in these solutions generally are negligible because they go to zero so quickly. So you might think, oh, I can forget about them, but you can't, and that's the problem. The thing that is, one thing that's particularly terrible about stiffness, you might think, oh, okay, well, there are so many bazillions of DEs out there. Some are stiff, some are not. You might think, how often does this happen? Well, I can tell you that any system of ODEs rising from a PDE, partial differential equations, where you're using a high spatial resolution, is stiff. Right? There's absolutely no getting around it. Because PDEs have derivatives with respect to time and space. What happens is you're discretizing derivatives in space to get that out of the way to reduce your PDEs to an ODE that only includes time. And that causes stiffness to occur in a system of ODEs. The higher your spatial resolution, which in these days of powerful computers, I know that's your summary, and the introduction to most of my papers these days, people expect to use high resolution to simulate physical phenomena, so they think, oh, I'll use a nice small delta x, and then they get a stiff system, and then their super powerful computer still needs a ton of time to solve it. And the thing is, so I guess I'll try to get my rant out of the way before I cover the rest of the material, because I could really go on about this if I wanted to, and sometimes I have. The problem is, to get around this, you need to address how you do time stepping. And all the time stepping methods I'm presenting, multi-step methods, Rowan kind of methods, they've been around a long time, some more than 100 years. And today, in real applications, we still basically use these methods. Now, there are certain bells and whistles we put on them. Like in the notes, I don't have a chance to cover it in this course because of labs and stuff, but one thing you do is adaptive time stepping. And that really does help, that you can vary your H over time from one step to the next and see if you can get away with something bigger and save yourself some time. But there needs to be a more fundamental examination of how time stepping is done, and especially if your system of ODEs comes from a PDE, and that, like I said, it's my whole research program that several of you in this room are either involved in or getting involved in, to try to actually achieve some separation between slowly moving components that dominate the solution and rapidly changing components that force you to use a small h, but you don't have to use a small h. It's not easy to do, and it can only be done in certain cases, but why not do it if you can? So, all right. So let's take a look at an example. What can happen with, even though it's a single ODE, not a system, but I have to be careful the time step you choose. So if y prime is minus 100y, and initial value of 1. So we know what the exact solution is, and that's just e to the minus 100t. So it decays to 0 very rapidly, but its derivatives are going to be through the roof, because you're multiplying by minus 100. So if you look at forward Euler, okay, we have yn plus 1 is equal to yn minus 100h yn, because your function is just minus 100y. So you're multiplying by 1 minus 100h yn. Okay. Let's see. Okay. So let's look at certain values of h. If I use h equals 0.1, so I go ahead and plug that in, I get, how does it simplify? Yn plus 1 is equal to minus 9 yn. So that means my numerical solution is minus 9 to the n times the initial value, which is just 1. How's that going to behave as a function of n?
So we're gonna oscillate, right?
It oscillates, but what else is it doing?
Getting bigger.
Bigger, because you have minus 9, then plus 81, then minus 729, and it just totally explodes on you.
I thought you were gonna say 4 points.
What?
Nothing. 729, times.
Oh, yeah, I'm too tired to do the multiplication in my head right now. 6,000 something, but
Yes.
or worse.
Well, 7290 minus 729. So 7290 minus 700 is what?
Yeah. I think about 6,500. Something like that.
6590.
Okay, all right.
6561.
I got the first digit right. All right, at least your brain is working. So it's definitely not like that.
Yeah.
It's supposed to decay to 0 and pretty rapidly. So, all right, let's do h equals 0.01.
Wait, so what did we learn from doing that?
But you have to be careful how you choose your h.
Okay.
Yeah. Well, let's let this run its course. Pick a smaller h. So now you get 1 minus 0.1. So yn plus 1 equals 0.9 yn. So yn equals 0.9 to the n. How does that behave?
How'd you get
Only
0.1?
0, right? 100 times
I'm sorry, what?
0.01 is
I got
1.
0, or the same as him.
Oh, I have 1 minus, oh, wait, do I? Hold on. Oh, yeah, sorry.
100, 0.
Didn't pay enough attention to my notes. Okay. Yeah, otherwise you would get 0. Well, at least it wouldn't grow anymore. Okay, now you get that. Yeah, I hate to say this, but you need to keep an extra eye on me today. Okay, how does that behave?
Decreases.
Yeah, not rapidly, but at least it's okay, getting warmer. And if you choose an even smaller h, then you'll get closer to the behavior that you would expect. Okay, so this, because this ODE has behavior of rapid decay, you need to use a smaller h, or because even though for Euler is a convergent method, has all the properties it's supposed to have, you have all those check marks, you still need to be careful about what h you use. Okay. Now, this ODE, y prime is a constant times y. It's very simple, we know how to solve it, but it's very useful for analyzing the behavior of time-stepping methods. So even though it's not the sort of ODE you actually solve numerically, it still serves a purpose. So we'll talk more about that. So y prime is equal to lambda times y. Y is 0 is 1, and the real part of lambda. So lambda is allowed to be complex, but we want the real part at least to be negative. This is called the test equation. So if you want to know how effective your time-stepping method will be, and how you need to choose h, try it on a generic test equation, and you get an idea of how stable it's going to be. Okay. Now, we know what the exact solution is. What is the exact solution? This nice separable linear DE. Yes. Okay. But the thing is, lambda is allowed to vary. So the larger the complex modulus of lambda is, the faster it decay to 0. Okay. So when you apply a one-step method, whether it's like Ford Euler or any Runge-Kutta method, because it's a simple linear equation, you always get something like this. Yn plus 1 is equal to some function that I'll call q of h times lambda times yn. So you're always multiplying by something. You saw this in Euler's method, but the same thing is true for other one-step methods. So you need this in absolute value to be less than 1. So the thing is, for any choice of lambda, you'd see, well, what h will cause this function to be less than 1 in magnitude. All right. Now, what does q of h lambda look like? What kind of function is it? It is a polynomial if your time-stepping method, if your one-step method is explicit. It is a rational function if it's implicit. Okay.
That's only for one step.
Only one step. I will talk about multi-step a little later on. Okay. Now, let's take a look at an example of a one-step method. So this is modified Euler, also known as the explicit trapezoidal method, as opposed to the implicit trapezoidal method that you dealt with on homework 1. Yn plus 1 is yn plus h over 2 f of tn yn plus f of tn plus h yn plus hf. Okay. So what you can do is we substitute our function f of ty is just lambda y, and see what simplifies a lot. So what we get is lambda yn plus lambda times only the y argument. So that's yn plus h lambda yn again. All right. So it turns out you can factor out a y sub n out of all of this. And let's see what we get. You get 1 plus, here we have h lambda over 2, and here again we have h lambda over 2. So it's h lambda. And then when you expand everything out, you get h squared lambda squared over 2. So 1/2 h lambda squared times yn. So this factor right here, notice, like I said, it's a polynomial in h lambda. It's a polynomial because this method is explicit. All right. Now, let's see. We need this to be less than 1 in magnitude. Well, when is that the case? So I'm going to simplify this. Look at function 1 plus x plus 1/2 x squared. So in other words, I'm going to assume that lambda is real, a real negative number. Okay. Now, if we were to graph this, and I only care about the left half plane, where x is negative. So for instance, if I plug in x equals 0, I get 1. So there's a point in the graph. The minimum, okay, so the derivative is 1 plus x. So the minimum of this function actually occurs at -1. Okay, so at that point we get 1/2. Okay. And then if I plug in x equal to -2, I get 1 again. So notice the function is always positive. Okay. So it behaves like this. All right. So the only time it is less than 1 only in this range from -2 to 0. So that's the case where lambda is real. Now if I allow lambda to be complex, I'm going to get some region of a complex plane I have to consider. But the point I want to make is, the larger lambda is, smaller h has to be to offset it. Okay. And as time-stepping methods go, it's a pretty severe constraint. Explicit methods tend to have a tighter constraint on h than implicit methods. Okay. All right. So a question on that one. Yes?
Where you got h times lambda in the middle, did you just do 1/2 of lambda yn plus 1/2 of lambda yn?
Yeah, this term and this term
Okay, I just
together.
wasn't sure.
Yeah. Okay. Now. Yeesh. Okay. All right. That's an example of a one-step method. Now let's look at how we examine this question for multi-step methods. So the inherent nature of multi-step methods complicates things a little bit. So what happens is, alright, so here's a general multi-step method. Here are alphas and betas. Okay. And you plug in a test equation. So Fn is lambda yn. So all the f's go away. Now we have only y's. So I can rearrange this, and we have a linear combination of y's, where I have alpha I minus h lambda beta I times these y values equals 0. Now, we saw a situation like this on Monday, where instead of dealing with the test equation, y prime is lambda y, we looked at y prime equals 0 to study stability for multi-step method to come up with a root condition. That was a recurrence relation. This is a recurrence relation too. It's just a different recurrence relation. So what we get is each yn can be expressed in a similar form as what we saw last time. We have some constant n to a power times certain roots raised to Vn, where these values mu1, mu2 up to mu s are roots of what is called the stability polynomial. Okay, so I use q of mu and h lambda, so it's a function of both. And it has this form, alpha 0 minus h lambda beta 0 mu to the s, alpha 1 minus h lambda beta 1 mu to the s minus 1, and so on, all the way down to alpha s minus 1 minus h lambda beta s minus 1 mu plus alpha s minus h lambda beta s. That's the constant term. Okay, so for roots, so this is a polynomial in mu. So the roots, which are mu values, determine the behavior of the numerical solution. So for what is called absolute stability, meaning that the solution decays to 0 as it's supposed to, we have to require that the roots of the stability polynomial, which are can be really complex, they must be less than 1 in absolute value. Okay. All right. So it's easy to get confused because it seems like we've just been down this road with multi-step methods and some condition on roots, but therefore for somewhat different purposes. So the root condition from Monday, that was just to be able to prove that a multi-step method converges at all as h goes to 0. This is for a case where you're not concerned about behavior as h goes to 0. You've established convergence. It's just that now you're choosing some non-zero h, and you want to make sure your solution is qualitatively correct behavior. So that's the distinction between the context in which you use this. And it's unfortunate that people use the term stability in both contexts, because that just adds to the confusion. So when I say just stability by itself, I'm talking about Monday stuff, the root condition. You're trying to prove convergence as h goes to 0. When I say absolute stability, that's what we're dealing with here. We're dealing with a stability polynomial, and for a non-zero h, and you want to know if that h is good enough, or when it's good enough. Okay, So I'll show you an example of how you come up with the stability polynomial for a given multi-step method. Dang it. Okay. So we'll look at three-step Adams-Bashforth method. So what's interesting is with one-step methods, your stability function that you're checking is polynomial if it's explicit, rational if it's implicit. But for all multi-step methods, explicit or implicit, you're dealing with a polynomial. So you have yn plus 1 is yn plus 8 over 12, 23 fn minus 16 fn minus 1 plus 5 fn minus 2. Okay, so this gives you beta 1. It's actually 23 over 12. This is beta 2. Yep. And this is beta 3. Beta 0 is 0 because this is an explicit method. This gives you your alpha 0, which is 1. This is your alpha 1, which is minus 1. So now with all those alphas and betas, we can form the stability polynomial. Okay. So what we have is, for our first term, we have alpha 0 minus h lambda beta 0, but that's 0, times mu cubed. So this is a three-step method. So that's the value of s sets the degree of your stability polynomial. So this is going to be a cubic. Okay, plus.
Why is alpha not yn plus 1?
I'm sorry, what?
Does it not matter? The alpha of naught and alpha 1. Why are they, should they be the other way? Yn and yn plus 1?
Oh, the thing is, index 0 corresponds to time level n plus 1. And then as you increase your index, you're going further back in time.
Okay.
Yeah, like for instance, if I had an fn plus 1, that would give me a beta 0.
Okay.
So yeah, that's why if you look at the general form, notice as this index increases, this index is decreasing.
Okay.
Although it's kind of infuriating that most books use that form, so I stick with that, but I've used some books, like the one for 772 that some of you might take in the fall, go the opposite way. And we need to get used to that. So. Okay. Next term is index 1. So we have
-1.
alpha 1 minus h lambda
23 over 12.
beta 1, which is 23 over 12.
Squared.
Yep, s squared. So you just keep knocking down, not mu squared, knocking down the power of mu. And then we have, well, there's no alpha anymore, so we get minus h lambda minus 16 over 12 mu. And then we have, there's no alpha, so it's minus h lambda 5 over 12 times the constant term. So if we go ahead and simplify all this, we get mu cubed plus minus 1 minus 23 over 12 h lambda mu squared plus 4/3 h lambda mu minus 5/12 h lambda. So that is your stability polynomial. Now, here's a problem with most multi-step methods. Once you have that, all you can do generally is compute the roots numerically. Like you pick a specific value of h lambda and see what the roots are. So for example, I'm going to let lambda equal minus 100, like in our previous example. Now choose h equal to 0.1. So this gives you a root. Mu is roughly minus 18.884. Way too large. We need the roots to be less than 1 in absolute value. So it is not absolutely stable. For that value of h, you need to pick a smaller h. So if we go ahead and do that, take h to be 0.005. Then the largest root in magnitude is roughly minus 0.924. So that is absolutely stable. So that will work. So you just have to compute. You have to, but barely. Notice it was still kind of close to 1 in absolute value. So you just have to pick your h small enough relative to your lambda. So for instance, in this case, h lambda was equal to minus 10, too much. Here h lambda is equal to minus a half, and that was okay. Right. So in any case, it's a product of the two that you're looking at, whether it's one step or multi-step. Yeah.
If we get like negative 0.924,
Yeah.
so then I know it's absolutely stable. We achieved our goals, but it's technically really close to 1, so we'd want to look for a smaller h.
Well, it's a trade-off because if you look for a smaller h, then your computation is still slower. You want the largest h you can get away with. So that's you're walking a fine line here. So you want to hit that sweet spot of fast computation but still correct behavior.
So like as long as it has an inkling of correct behavior,
Yeah.
we quit because we don't want any more computation there.
Right. Yeah. But you got to make sure on the right side of the line, or your solution's useless. So you want to have a little margin of error. You err on the side of smaller h.
Okay.
Yeah, because otherwise your solution is crap.
The h affects the computing time,
Yes.
but what does the lambda?
Well, it's actually the product of lambda and h, because here, well, the point is, if I have a lambda that's pretty small, I can choose an h that's pretty large.
Right.
So it's this product we're keeping our eye on.
Okay, but there's no like physical part that lambda, like it's not the computing time or it doesn't. It goes into the computing.
Yeah. Because for instance, let's suppose we're solving PDEs. The finer your spatial resolution for your PDE, the larger your lambda is going to be. Therefore, you need a smaller h. Even though the underlying problem you're solving is the same. Okay. So in general, for one step or multi-step, implicit methods can use a larger h, generally speaking. In fact, in some cases, there's a couple nice methods where the h actually doesn't matter. You can pick it as big as you want, and you'll still get correct behavior. But you're doing more work per time step. Because you have to solve solve a nonlinear equation. Using some of the iterative methods that I talked about last semester, like Newton's method or secant method, something like that. Okay. And the point is, whichever method you use, you're solving it iteratively. So you're computing yn plus 1, you have an initial guess for it. And you compute several values. So one time step for an explicit method equates to work of multiple steps for an implicit method. And now the thing is, the smaller h you pick, the better your initial guess. So fewer iterations you'll need. So So that's something that can help. But because at least with time stepping methods, you have a natural initial guess. If you want your initial guess for yn plus 1 could be just yn. It's already pretty close. Or maybe you can do a forward Euler approximation to get an even better initial guess. Something like that. Okay, so there's a trade-off here, and you have to make a judgment call, which is a better way to go. Okay, in fact, in the notes, this is page 317, I have Newton's method. So if you apply Newton's method to carry out a time step of an implicit multi-step method, a general multi-step method, what's actually involved with that? Because you can say, here's the equation you're actually trying to solve as a function of yn plus 1. Yn plus 1 is your variable, and you differentiate in respect to that variable. So the computation itself is not that involved, except you have to plug into your f several times. Okay. So the algorithm is given there, but during the last 15 minutes that I have, whoa, okay. 2 dozen of my pages, yes. Okay. I have a page and a half, I think I can pull this off. Okay, so use this time to say a little bit more about absolute stability. Okay. So first, some terminology. The region of absolute stability is the subset of the complex plane, so the set of all complex numbers, where you have absolute stability. So you have q of h lambda is less than 1 in absolute value for the one-step methods, and you have the roots of your stability polynomial are less than 1 in absolute value for multi-step methods. So whichever scenario applies, where h lambda is small enough to allow that to happen. Okay. Now, you want a larger region of absolute stability. And like I said, generally, implicit methods have a larger region of absolute stability than implicit methods. Okay. Now here's the, now for example, Euler's method, or sorry, forward Euler, well, you have yn plus 1 for test equation is 1 plus h lambda yn. This is your q of h lambda. So it turns out that the region of absolute stability is just a disk where you have 1 plus h lambda less than 1. And in a complex plane, I can draw that for you. You have a disk that is centered at -1, and it has a radius of 1. So that's it. That's all you get. Okay, so like in a real case, h lambda has to be strictly between 0 and -2. Okay. Let's take a look at backward Euler. Similar method. Yn plus 1 is yn plus h lambda yn plus 1. So now, if I rearrange that and solve for yn plus 1, I get a rational function, 1 over 1 minus h lambda yn. So this is my q of h lambda. Okay. Now, if I keep in mind that lambda has a negative real part, so h lambda as a whole has a negative real part, when is this going to be less than 1 in absolute value? So the negativity is important. H lambda, so think of h lambda as a negative real number, if you want. So when is that going to be less than 1? Always, yes. Because the minus becomes a plus, so the denominator is always going to be larger in absolute value than the numerator. So, for all lambda with negative real part. So if I were to draw, right, so I'll shape this in for forward Euler. Now if I do backward Euler, what am I going to shade in? The entire left half plane, where h lambda is negative. And that will take a while.
Just the entire
Yeah.
left-hand side?
Yes. Because you're still dealing with complex numbers of negative real part.
So many negatives.
That's a complex plane.
Yes.
The negative complex.
Yeah. Well, it's region of C. Yeah. Okay. Yeah, 'cause this is a real and imaginary axis of h lambda taken together as a single complex number. And just for you guys to answer this question, I allowed you to let h lambda be real. Just do the algebra in your head, but it applies just as well if it's complex. Yeah, so it's all of this extending forever. Well, that's a way better situation, obviously. Backward Euler is a very special, narrow class of methods where the region of absolute stability is equal to the entire left half plane. And we love having that. Okay. Unfortunately, it doesn't happen very often. So there's a name for that. Okay. So same method is astable if its region of absolute stability is equal to the set of all complex numbers h lambda such that the real part of h lambda is negative. So the entire left half plane. Okay. So backward Euler is astable, as I just showed. Another is implicit trapezoidal method. Because what happens in that case, you have y plus 1 is yn plus h over 2 fn plus fn plus 1. So if you rearrange this, so you let this equal lambda yn, and this is lambda yn plus 1, and you rearrange, you get yn plus 1 is equal to 1 plus h lambda over 2 over 1 minus h lambda over 2 times yn. And the thing is, same reasoning applies as of backward Euler. Because h lambda has a negative real part, the denominator is larger. So you can choose h lambda to be as large as you want. But tell me something, suppose I chose h lambda to be particularly large. What kind of strange behavior would I get in that case? So imagine that h lambda is so large that you can neglect the ones. Oh, what would the method simplify to in that case? Negative 1.
Negative 1. Well, yeah.
Yeah, oscillation. And I think we talked about this on Monday. Something like it came up where you can have a higher order method. This is second order accurate. But sometimes when you get that high order, if you don't use it carefully, you can still get non-physical behavior. I don't remember the context which it came up.
Like weakly and strongly.
Yes, exactly. Yeah, that was it. Because Simpson's method, high order accurate, but weakly stable. You could get behavior like that if you're not careful. So, okay. So both of these are astable. Okay.
Does that only happen in like implicit methods?
Actually, about to make a statement about that. About astable. So there are. But yeah, so astable methods are, or any other region methods may be astable, but has a larger region of absolute stability. They tend to be used for stiff problems. So in the last 6 minutes, I have a few very interesting theorems. Actually, I don't think I presented in this class before. I normally save them for 772, but
Ready?
what?
Are we ready for that?
I'm only going to state them, not prove them. So. I know, if you guys think 772, we can try proving them too. If there's time. Okay. All right, so these are theorems due to German Dahlquist, the foremost numerical analyst ever. Unfortunately, he has passed away. Has an excellent book on numerical analysis that I think I might have somewhere. Or theorems, there's multiple of them. Okay. Okay, there are 3 of them. I'll just state them, there's not much to it. So first is called they all are named after Dahlquist. So first is the equivalence theorem. Okay. So the equivalence theorem says, says that a consistent, and I basically stated something along these lines last time, but this is where it really comes from. A consistent multi-step method with its local truncation error of order h to the p, so it's p order accurate, is convergent with its global error that's the same order h to the p, if and only if it is, I said the term I used last time was simply calling it stable. Another term for it that might help distinguish is zero stable, and this is from Monday. In other words, it satisfies a root condition. So this is not about absolute stability. Okay. Okay. So this is the way of formalizing Stephen and me last time, that consistency plus stability gives you convergence, and then the global error is the same order as the local error. Okay. All right. Now, the next theorems are called barrier theorems. Barrier because they highlight limitations of multi-step methods. So we have a first barrier theorem, which says that the order of accuracy of a zero stable, so again, not absolute stability, multi-step, S-step method, so we're talking about multi-step, is at most, well, it depends on S. S plus 1 if S is odd, and S plus 2 if S is even. So that's the best you can do when it comes to order of accuracy of a multi-step method that satisfies the root condition. For example, Simpson's method. It's neither Adams nor BDF. It is a two-step method that is weakly zero stable, but it's still zero stable, and it hits the maximum possible order of accuracy of 4. Right. So you can have a multi-step method that violates these conditions and has a higher order of accuracy than its warrants, but then it's not zero stable at all. It does not satisfy the root condition. Okay, and finally, okay, I have 1 minute. The second barrier theorem which is kind of it's a real bummer of a theorem actually. And this actually gets to your question. There is no such thing as an explicit astable method. Okay. And then the other condition, so that's, I guess we'll call it part A. Another statement it makes is there's no such thing as an astable method that has an order of accuracy greater than 2. So we have the example from a little while ago, the trapezoidal, implicit trapezoidal method is second order accurate. That is the best you can do and keep A stability. And finally, of all second order accurate, astable methods, the implicit trapezoidal method has the smallest error constant. So in other words, a C that goes in front of the H squared. And that's among all methods, multi-step methods that are astable and second order accurate. So I guess you can describe these like on a continuum, and then and describe the error constant when it's continuum, and it happens to be minimized when you get to implicit trapezoidal method. Okay. So really, what we're saying is the method I've just shown you, implicit trapezoidal, is the best at combining order of accuracy and stability in a way, because you have a whole left half plane, at least it's second order accurate, you can't do any better than that. Okay, and that concludes discussion of solving initial value problems. So linear algebra next, brought to you by Amber. So.